Hello, and welcome to part two of our lecture video series from Wednesday, March 1st, where we're talking about covalent bonding and the Lewis dot structures that we use to describe covalent bonding. So before we get into drawing more of structures like we've seen here, I want to talk a little bit about the Lewis model and what it is, how it operates, and some language you'll see when we start applying the Lewis model to represent how atoms come together to form covalent bonds. So the Lewis model of bonding is a representation, and it can be used for ionic bonds as well as covalent. So I'm going to say it's a representation of chemical bonding where valence electrons are drawn as what we call dots around an element symbol. And as we know, these dots or electrons can be donated or accepted to form an ionic bond, which is just that electrostatic attraction between the positive and negatively charged ion. Or our electrons can be shared between atoms, and this is what we call a covalent bond. So when we are drawing our Lewis dot structures using the Lewis model, these dots or electrons are going to be shown as being given away or accepted from one element to another, forming thus an ionic bond, or we're going to show the means by which they are shared, like we did up here for H2O. Now remember, the entire driving force behind both of these bonding schemes is we are trying to become stable, meaning we are trying to achieve octet or duet if we are hydrogen or helium. So this is all a question of energetics. So let's talk some language that you will see and some symbolic stuff that you will see when drawing Lewis dot structures. So you will see things like an electron is represented by a dot, specifically a valence electron. In covalent compounds, you will see a line to represent a covalent bond, where by definition, a covalent bond or a bonding pair is always a shared pair of valence electrons or two valence electrons that are shared. So if we go back up here to our H2O example, if we were to use the Lewis model, these shared valence electrons here, instead of being drawn as dots, would then be drawn as a line, where the line is the covalent bond. You will also hear me refer to this as a bonding pair. Some other things that you will see is you will see electrons that are drawn next to one another that are not involved in a chemical bond, meaning they're just kind of left over as a result of being present on their parent or original atom. So that'd be these blue electrons here on oxygen. So anytime you see two dots drawn side by side like this, these are what's called a lone pair. And you will hear me refer to this as a non-bonding pair. Now I will make a note. Sometimes atoms can form more than one covalent bond to one another, meaning they can share more than just two electrons. So if atoms share multiple electron pairs, then they can create stronger and also shorter bonds. So let's look at how we might draw that. So if I've got two lines drawn like this is still a covalent bond. This is now called a double bond. Still covalent, but it is a double bond, whereas up here, a single line is implied to be a single bond. And we call it a double bond because we have two shared electron pairs between our atoms. So this would be like if oxygen up here could somehow share with one of these hydrogen atoms yet another pair of electrons. We know that isn't the case because our hydrogen atoms have only that 1s orbital that could be filled. But in the instance of kind of more complex elements and compounds that have more electrons that need to be kind of swapped around and shared and such in order to achieve stability or octet, sometimes we will need to share more than one electron pairs. So we'll call this two bonding pairs. And remember, a chemical bond in and of itself, by definition, is just some strong association between atoms that allow them to stick together, so to speak, and form compounds. So if we are sharing not one but two electron pairs, there's a higher degree of association between our elements, and thus this bond is stronger than just a single bond. We can also see something like this, which is a triple covalent bond, which involves three shared electron pairs or three bonding pairs. And since our atoms would then be sharing 6 total combined electrons between them, right? 3 electron pairs, their degree of association in a triple bond scenario is even stronger. So this type of bond is stronger than even a double bond. So if I were to kind of rank them, I would have my single bonds being weaker than my double bonds being weaker than my triple bonds. So weak or small or low association. And over here, strong or large association, because there's a greater degree of sharing or covalency in the triple bond compared to my single bonds and double bonds. Now you will notice I have taken care to draw these in a particular way. Anytime you have more electrons that are being shared in a covalent bond to form things like double or triple bonds, what you're going to see is that your atoms are then bound closer to one another. And we're going to describe why this is when we go to like the true model of bonding. Lewis is like a nice little shortcut where we can pretend that quantum mechanics doesn't exist. But for now, all you need to know is that the single covalent bonds are long, double bonds are short, and triple bonds are even shorter. Because we have atoms that are closer together. The analogy that I like to give for thinking about a single bond versus a double bond versus a triple bond is imagine that you had a piece of rope on a stranded, deserted island, right? And you had no means of cutting your rope or fabricating new rope, but you need to make a rope that is 2 times as strong. So like if you were to hold, I don't know, say like a charging cable out in front of you, if you were to look at that charging cable and figure out how you can make it twice as strong, you might imagine that you could fold it in half. Sure, in folding it in half, you would have a stronger cordage, but you would also have half as much. If you were to do something similar to try to get a rope that is 3 times stronger, you might fold your charging cable into thirds. And in doing so, you would of course have a really, really strong cordage, but you would have a cord that is now 1/3 of its original length. So because we've got such strong association with our triple bond, it's going to be a shorter distance between our atoms that are sharing those valence electrons. Now, last thing that I'll say about this before we start putting this all into practice and making our Lewis dot structures is that each of these covalent bonds are counted or treated as one bond. So like if I had an element X bonded to element X via a single bond, this would be one bond made up of 2 shared electrons, bonding electrons, etc. We could also think of this as one bonding pair. If I were to have some elements X brought together using a double bond, this is still also one bond, but it is one bond that is consisting of 4 total bonding electrons, or 2 bonding pairs. So this is still just one bond holding them together. It's just one bond that involves a higher degree of sharing or a higher degree of covalency. And then lastly, if I had 2 elements that were triply bound together, this would still count as one bond, but it is comprised of a total of 6 bonding electrons, or shared electrons, or 3 bonding pairs. Because recall, each line in the Lewis system is going to represent a shared pair of electrons. So now that we know some of the verbiage and some of the signage that we'll see in Lewis models, let's go ahead and begin to start building some. So we're going to start off with Lewis structures for atoms, monoatomic ions, and let's also do some ionic compounds, even though I don't really think those are that interesting. And then from there, we will move on how to draw Lewis structures for covalent compounds and hopefully get some practice in on how to do that. So I will see you in lecture video 3.